All right, welcome back to AP Calculus. This is chapter 5.2 in the book. The topic is mean value theorem, and I'm going to start with a picture. Here is some function, and here is a point where x is equal to a, and here is another point where x is equal to b, and the function is f of x, and so then obviously that y value is f of a, this y value is f of b. And I can draw a secant line through these 2 points. This is called a secant line, any line that cuts 2 points on a curve. And I know that the slope of this line is the change in the y value divided by change in the x value, which is f of b minus f of a divided by b minus a. We've also, here in calculus, referred to this as the average rate of change between A and B. So the average rate of change. Now, here's what the mean value theorem says. The mean value theorem says that if f of x is continuous on the closed interval AB and differentiable on the open interval AB, then there is some value of C, and C has to be between A and B, such that the instantaneous rate of change at that point is equal to the average rate of change between A and B. So let's go ahead and write this down. The mean value theorem is defined as follows. For f of x continuous on the closed interval AB and differentiable on the open interval AB, there exists some value of C, which is in the interval AB, such that the instantaneous rate of change of the function at that point C is equal to the average rate of change of the function between B and A. I can't emphasize this enough, guys. It has to be a continuous function. It has to be a differentiable function. Let me show you two examples of what happens when it isn't. First of all, let's take the following function. I choose 2 points, closed interval, -1 and 1. This is continuous, check, differentiable, no. The average rate of change, f of b minus f of a divided by b minus a, is 0 between those two endpoints. There is no value of c on this function such that f prime of c is equal to 0. Fail due to lack of differentiability. Example number 2. Discontinuous function. Continuous? Nope. Differentiable? irrelevant because we've already failed, and let's see what happens when we try to apply the mean value theorem. When I look at this, if I take the slope of this line I'm not happy with this example, so I'm going to cut this bit out and use a different example. Let's look at another function, which is discontinuous. This is A, this is B. Notice, so this fails the continuous function. And we're not even going to worry about the differentiable part because it's already failed the continuous. And let's see what happens. If I take the secant line from A to B, clearly f of B minus f of A. By the way, this is the floor function, or int of x. And we're going from 1 to 2 here. And so we know that this is going to have a slope, oops, B minus A. And the slope is equal to 1 in this case. But if I look at the function itself, f prime of c is equal to 0 at all points between a and b. It's never equal to 1. It's always equal to 0. And we don't have the derivative here, so that doesn't matter because we've got that jump. The continuity means it failed. Now, could you have a function that had a point in the interval where the slope was equal? Yeah, absolutely. But the mean value theorem says there has to be a point. And clearly what we've seen here is that we can't even talk about the mean value theorem in either of these cases because the mean value theorem doesn't apply. All right, so let's look at some examples of the actual mean value theorem in play. So we've got y equals x squared on the interval 0 to 2, and we need to find the value of c. So first of all, does the mean value theorem apply? Well, the answer to does it apply is yes. This is a continuous function because all polynomials are continuous. It is a differentiable function because all polynomials are differentiable. So we've got f of 2 minus f of 0 divided by 2 minus 0. That is 4 divided by 2, which is 2. So the question is, do we have f prime of c equal to 2? The mean value theorem says, yes, we do. So we're done with that part. Have we proven that there must be a value? Yes, we have. Now, the only other question is, where is it? F prime, right, pen quit working. I have to reset the pen. We know that the derivative of x squared is 2x, which means that 2c must be equal to 2, which means that c must be equal to 1. Right here, there's the point. The slope of this line right here is 2. So if you are in my classes, why don't you go ahead and do exercise 1. You can pause the video, go away and do exercise 1. My class was making fun of me for sometimes pausing myself and sitting for just a second, and sometimes actually pausing the video and then coming back again. So this time I won't do that. I'm going to dive right into example 2. And in example 2, I'm going to explain why some functions fail to satisfy. The mean value theorem fails on the interval -1 to 1. So let's look at 2 functions. The first is f of x equals square root of x squared plus 1. So taking the derivative, f prime of x equals 1/2 x squared to the -1/2 times 2x. Rewriting this, we get x over the square root of x squared. And this derivative does not exist at x equals 0, which means that it fails due to the fact that it's not differentiable. Now, might there be a place where the slope of the function is equal to the average rate of change between -1? There may well be, but I can't say that there is because the mean value theorem has failed. I would have to go do some exploring and see if I could find one without any idea of whether it's even there or not. Second question, let's look at a piecewise function, f of x equals x cubed plus 3 for x less than 1 and x squared plus 1 for x greater than or equal to 1. And analyzing this function, what I notice is that the limit as x approaches 1 from below of this function is 4. We're using the first half of the piecewise function. The limit as x approaches 1 from above of this function is 2, using the other half of the piece, the top half of the piecewise function, which means that this function is not continuous. So again, there may be a place, a value of c such that f prime of c equals f of b minus f of a over b minus a, dot, 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 etc. But I can't say there must be because the mean value theorem does not apply to this. I would have to go and experiment and do some math and maybe find that place, but I'm going into the problem without any idea of whether or not it even exists. All right, my students, do exercise 3. And here we go with the next one. Example 3, mean value theorem. F of x equals the square root of 1 minus x squared. And we're going to do this across the interval -1, 1 again. And the question is, we want to find the equation of the tangent line. So notice that I'm doing the same process, but then we're just taking it an extra step by finding the equation of that tangent line. So f prime of x equals 1/2 1 minus x squared to the -1/2 times -2x. We get a derivative of -x over square root of 1 minus x squared. Are there any places where this function is not continuous? Well, okay, let me back up there. Sorry. This is a continuous function. We know it's a continuous function. It is valid for all values of x inside that interval. If you go outside the interval, it doesn't exist. So it is continuous in its domain. So check, we've satisfied the first condition. Is it differentiable? And notice that the derivative exists for everywhere in the open interval. I can't plug in 1 or -1 into this, but it doesn't matter because the question is it differentiable in the open interval? Check. Mean value theorem does in fact apply. And so now here's what we need. We need to know what the secant line slope is. And that will be equal to f of 1 minus f of -1 divided by 1 minus -1, and that's equal to 0. So we're looking for f prime of x equal to 0, and we get that x must be equal to 0. And we're just doing that by inspection, since the denominator has to be equal to 0 to make this true. The only possibility is that x is equal to 0. So then the question is, what's the equation of this line? Well, the secant line has a slope of 0, and so f of 0 is equal to square root of 1, which is 1, which means that the secant line has the equation y equals 1. And why not plus or minus 1? Well, if we look back at the original function, we're only dealing with the positive root of this function. Okay, go ahead and do exercise 9. I have somehow turned on a flashlight. I have no idea what this flashlight thing is or why it's doing this. This is a bit frustrating. Go ahead and do exercise 9, and we will then talk about the physical interpretation. Oh my gosh, this is so annoying. I don't know why my cursor is now making a little flashlight. Okay, physical interpretation. What do we mean when we say, does the mean value theorem apply, and what does the mean value interpretation? The instantaneous rate of change. Oh my gosh, this is so annoying. At some interior point is equal to the average rate of change between the endpoints. Again, drawing that graph, we've got two endpoints outside of which we're not dealing with the function. We draw a line representing the average rate of change between those 2 points. We calculate the slope, and therefore there must be a point inside which has the same slope, which is the instantaneous rate of change. That one must be equal to, so sorry about this stupid flashlight thing, must be equal to that one. And again, assuming that we are dealing with a continuous and differentiable function. Okay, that's the end of this video. Thanks for watching, and we'll come back with some examples of how we use this and what some of the ramifications are.